Okay. So, welcome back. We are basically discussing transformation based strategies, and last week we talked about a very important transformation Shapiro reaction, and we said that transformation based structural starting material based as well as functional group based strategies can be combined together, and today we will try to continue in the same area transformation based strategies, and the problems which I have picked up now. The target is something like this. You have a cyclopentanone based starting material, and I said here I give you the starting material, and the target I said you have to make a exocyclic methylene compound from this starting material, remaining part all remain same. Now, I said the prerequisite is you cannot use a Wittig reaction. You cannot use a Wittig reaction. Wittig reaction all of us know. So, basically you need to know some reaction, some transformation without Wittig, and that is the beauty that there are many other transformations is available in the literature where you can create carbon carbon bonds without using the Wittig reaction. Now, this particular transformation demands that your starting material having a free alcohol. So, as I said, the free alcohols are normally not kept as intact. So, you can think about protecting the free alcohol, So, you start with protecting the free alcohol. Now, as we have not discussed the protecting group chemistry yet, which we will be discussing later on, you just put PG. PG stands for protecting group, which is a suitable protecting group for alcohol, any suitable protecting group. We will be discussing these things little bit later on. So, first protect the alcohol as it is a simple protecting group, we put PG. Now, I said you cannot use a Wittig reaction. The reaction which we will be using here now is named as Peterson Olefination. Now, Peterson Olefination is a similar kind of reaction of Wittig type reaction. Now, the reagent which was used here is a trimethylsilyl CH2 MgCl. Now, the reaction is basically similar. TMS CH2 MgCl means you have a TMS CH2 minus and MgCl plus. So, the first step is basically you will be OPG is here and you will be getting O minus, your TMS CH2 basically attacks to the carbonyl here and you get CH2 TMS. The situation demands next step is basically elimination of this silicon group as well as this oxygen, okay. And this elimination can be done in both ways. You can do it a acid elimination, acid mediated or base mediated elimination. Usually acid mediated elimination is simple mineral acids was used, and base mediated sodium hydride or potassium hydride was usually used. And the as I said, the mechanism you need to find it out in the scene archive, because if you focus more on the mechanism part here, then we will be losing tracks. So, fine, eventually in the slides which I will be giving you as supplementary materials, you will find the mechanism there. So, Peterson Olefination will basically give you a this kind of simple elimination. Usually it was found that it can be undergoing a acid mediated reaction as well as base mediated reaction. Now, next what you need to do, you just need to remove this PG. Depending on the protecting group, you can basically use the reaction condition. So, this is your now the product molecule. So, Peterson Olefination is a very important reaction and which will be give you the olefin without using the Wittig reaction. You are basically making a new carbon carbon bond by using a Peterson Olefination. This is a purely transformation based approach, and try to focus it out wherever you find similar kind of target molecule given, that you need to make a carbon carbon pi bond then you can use Peterson Olefination as a suitable replacement of Wittig reaction. The next target was a similar kind of target, again based on a transformation which is, I will give you the target. This is the target molecule, the transformation I will be also giving you the starting material. You will see the starting material and try to correlate. This is how the starting material can be correlate with this final product. Now, you see the starting material is a cyclohexanone derivative, okay, and the final product you have almost similar kind of structural network. Both these gem dimethyl groups are here, but the ketone group has been changed its relative position. From here it came into here, as the starting material is here, it basically came into here to here, and one extra methyl group was added. So, the target molecule has one extra methyl group. This reaction, if you are not familiar with a suitable transformation, the transformation which we will be now talking about is named as Babler oxidation. Babler oxidation is a bit uncommon transformation. Now, see, as I said that in the target molecule you have a one extra methyl group. So, you need to introduce a methyl functionality. The starting material is something like this. So, we will put a methyl lithium or methyl magnesium first. Now, as I said, until and unless you know the Babler oxidation, this transformation is difficult to visualize. So, you first do a methyl lithium addition and you will get this corresponding Grignard addition on a alpha beta unsaturated ketone. Is a 1,2 addition, is a 1,2 addition. This compound can undergo 1,4 addition, but we have done a 1,2 addition. 1,2 additions are very hard. We did not do a soft addition like copper things that will promote the 1,4 addition, fine. Now, if you try to correlate the carbon network between the target and this intermediate, everything is similar. You have 3 methyl, you have 3 methyl, only thing is the ketone group position needs to be rearranged. Now, tertiary alcohol, as I said, these compounds are very inert. Tertiary alcohols won't undergo oxidation because they do not have a abstractable hydrogen here. Now, here the Babler oxidation is a important reaction. Babler oxidation is basically a oxidative transformation where you treat a tertiary allylic alcohol with chromium based oxidizing agent. You can take simple chromium based oxidizing agent. Now, what happens? It basically gives you a initial step, you will get a chromate ester. So, put the methyl here O Cr double bond O O minus, the chromate ester which is the first intermediate. Now, if you have a close analysis of the structure, you will find that this allylic double bond plays an important role. Is a 1 2 3, is a 1 2 3. There is a kind of a, you just do a room temperature reaction, so thermal reaction. The 3 sigmatropic rearrangement takes place, that is why it is called oxidative rearrangement. And then you find this oxygen is transferred from this chromium to this allylic position, which is the final target molecule. So, now you do the oxidative transformation, what you will get? The double bond from this position now has been migrated here and you get a oxygen chromium bond. The remaining part remains same. Now, see, the framework has been almost achieved. The framework has been almost achieved. Okay. Now, eventually you have a abstractable hydrogen here, which is the essential prerequisite of chromium based oxidation. Now, this oxidation will takes place, and now basically you will get the desired target molecule, which was So, Babler oxidation is a very useful transformation, we called it a oxidative transformation, but the prerequisite is for Babler oxidation you need to have a allylic tertiary alcohol, allylic tertiary alcohol. So, in terms of potential retrosynthetic disconnection, Babler oxidation can be regarded as, let us say I am drawing a simple allylic alcohol, simple ROH. This is a potentially 3 degrees or tertiary allyl alcohol. This center is having all carbon and 1 oxygen. Okay. Then you subject to this reaction to chromium trioxide, the Babler oxidation. The disconnection now what we will get? We will basically get this kind of alpha beta unsaturated aldehyde through a similar kind of mechanism. So, whenever you are trying to have a alpha beta unsaturated aldehyde of this kind of structure, you can try to think about a Babler oxidation protocol starting from this starting material. So, Babler oxidation was very useful for giving you alpha beta unsaturated compound depending on the reaction condition. Now, based on the same Babler oxidation, our next problem was framed. The next problem, the structure is a little bit complicated, is a 5-member cyclopentane ring, and then you are having it a 7-member ring, is having a 7-member ring CH2, CH2, CH3, and in addition you are having a methyl group here. This is a target molecule. Target is bit complex, but the hint is we will be using a Babler kind of oxidation, okay, but simplified version I will give you the starting material, that what starting material will be we using. We will be using a starting material this 2,3 dimethyl cyclopentanone, which is here methyl methyl, and this part the ketone group has been basically replaced. And also I will give a starting material which is similar. Is a vinylic iodo as well as aliphatic iodo. That was starting material was given to you. Now, if you do a retro now, you try to correlate this part is basically your this starting material, okay, and this part is CH2, CH2, CH2 is CH2, CH2, CH2. Only thing is you need to introduce these things now. So, initially we will do a lithium diisopropyl amide, which is a base, which is a non-nucleophilic base. Now, this compound we will try to abstract this hydrogen in thermodynamically controlled enolate. The enolate which is most stabilized under this condition will give you this, fine. And then you have a electrophile here, you do a electrophilic attack out of vinyl iodo and this aliphatic iodo, this is more active. So, basically you will get a product methyl CH2, 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 we have a 3 carbon and then your iodo remains same. So, you get this product, fine. Then what we need to do, we will basically next try to do a, taking the starting material, we will subject it to a butyl lithium treatment, which will basically give you this vinylic iodo to a vinylic lithium species. You put a CH2, CH2, CH2 and then CH2, 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 then you try to put this vinylic lithium. Now, this vinylic lithium will undergo intramolecular nucleophilic addition. to give you the 7-member ring which was required. So, now try to draw this thing. So, after intramolecular nucleophilic attack and acidic workup, you will basically get. Now, try to put CH2, 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 1, 2, 3, yes, and then you have this methyl, this methyl. Now, potentially look to the target molecule when you earlier discussed. Now, what is this compound? This compound is a tertiary alcohol, tertiary allylic alcohol. Now, you subject to this Babler oxidation. By following the similar kind of mechanism, now this compound will give you the target molecule whose structure is the same which is desired by us. And now, basically this O chromium ester 3 sigmatopic rearrangement, this double bond will basically migrate it here, and then basically you will get a this kind of structure. With this ketone now come to this allylic position, 1, 2, 3, these things. So, this is your target molecule which was given at the initial point. So, until and unless you are quite familiar with this Babler oxidation, this potentially useful transformation is very difficult, but eventually now you know that Babler oxidation, and you can now formulate the alpha beta unsaturated compound can be easily generated from tertiary allylic alcohol by a oxidative transposition or transformation. So, I call this as a oxidative rearrangement or oxidative transformation, oxidative rearrangement, and this is the Babler oxidation which we are discussing. So, Babler oxidation is potentially very useful reaction, and this reaction can be done in with extreme efficiency, and that will give you a good potential useful reaction. So, couple of new reactions we are basically getting familiar. The next target was a very simplified target. Do I need to give the starting material? Yeah, let us see. If I give the starting material, then probably your job will be little bit easier. And I said I will be giving you a starting material like cyclohexanone. It is a very simple straightforward approach. Probably at the very beginning you can think about is a alpha beta unsaturated compound. So, is normal aldol kind of dehydration will give you the product. So, if you do a retro something like this is very familiar to all of you. So, you can have one of this compound as a intermediate, and you can do a aldol transformation. Fine. Now, what you need to do? You need to cut down to the starting material or go back to the starting material. How the starting material? So, it is fine. This you can just want to use a alkylation reaction by using monobromoacetone. You treat a basically it is called a base mediated alkylation, which is the main transformation, base mediated alkylation. Okay. Now, here there are other ways also, other ways you can do. I said that if I give you a prerequisite that you cannot use aldol reaction as a main disconnection, I will have another retro which will now I will discuss, and this retro is little bit adventurous, and then we will try to find it out that how this retro is possible. We said a Wittig type of reaction can also be thought about. Now, this compound is a named as phosphonate, and the transformation we are looking for a Horner-Wadsworth-Emmons reaction. In a standard Wittig reaction, what we do? We react a aldehyde or carbonyl compound with a Wittig halide, but here we will be reacting a aldehyde or carbonyl compound with a phosphonate esters. Now, phosphonate esters is basically something like this. The mechanism is in principle similar. You need a carbon containing group attached to the phosphorus, which is having abstractable hydrogen, and if the reaction occurs in presence of a base, you basically get a you basically get this minus attacks here, and you basically get this particular olefins. But depending on the phosphonate which you choose, that basically gives you what target you will be getting. Now, let us coming to the problem which was given to you. You take the cyclohexanone, and if you having a phosphonate, first you do a as if you have this starting material and this phosphonate. Now, this phosphonate has two part, one part is the bromo part. So, first treat the base mediated alkylation. So, minus this comes here will give you a CH2 these things, and then your ketone is there, and then you are having this P double bond to OMe. Now, this methylene hydrogen you can basically much more acidic adjacent to the ketone as well as the phosphonate. Now, it undergoes intramolecular Horner-Wadsworth-Emmons reaction, HWE Horner-Wadsworth-Emmons reaction. So, please go to the scene archive to have a possible mechanism of this Horner-Wadsworth-Emmons reaction. Then you may ask that, sir, how you can make this compound. This also easily can be done. This is a purely transformation based approach, and you can do it. We will explain these things little bit later on. Okay. Now, these compounds can be commercially available, or even you can make it. The best way to make this compound is basically starting from this kind of compound. You take this dibromoacetone and react to it trimethyl phosphite. This is a transformation named as Michaelis-Arbuzov reaction. Michaelis-Arbuzov reaction. You can search in the scene archive to get an idea of Michaelis-Arbuzov reaction. So, that is basically a very nice reaction, and is a equivalent to this Michaelis-Arbuzov reaction is a very good reaction which will give you the corresponding ketophosphonate. Now, with this ketophosphonate you can do a Vedic type of reaction which is named as Horner-Wadsworth-Emmons reaction. Now, what are the reactions we now learned till date? We have talked about this Babler oxidation is very useful, Shapiro reaction, Horner-Wadsworth-Emmons reaction, Peterson Olefination. So, all are basically kind of a very new transformation, and particularly this Horner-Wadsworth-Emmons reaction, Peterson Olefination are basically carbon-carbon bond forming reaction. So, transformation based approach are basically dealing with different kind of transformation which are key transformation. Key means single step transformations. The next transformation based strategies which we will be talking about is a transformation based on a very unique reaction, and this I am sure all of you know it. This we have already discussed couple of times. I will be giving you a target something like this, and I have given you the starting material also. Starting material was given to you. This is simple, we have already discussed it. If you now go back to the earlier lecture notes, this is alpha, beta, gamma, delta unsaturated compound. It is basically a gamma delta unsaturated compound. So, gamma delta unsaturated compound straightwise you can think about doing a Johnson orthoester rearrangement. The starting material is a allylic alcohol, starting material was given to you. So, now subject to the our known reaction Johnson Claisen rearrangement or Johnson orthoester rearrangement, it will basically give you do this reaction in your leisure time and will find the compound which will be you will be getting is this compound. So, now what is this? Is a alpha, beta, gamma delta and is a gamma delta unsaturated esters. Now, try to correlate with this target molecule. The target molecule only thing is you require a extra ketomethyl group. Now, we said esters are highly reactive. If you react with Grignard reagent, they will basically give you excess Grignard addition. So, we will be trying to convert these esters to a less reactive compound and normally we do it through a amide. Now, this particular amide is named as Weinreb amide, Weinreb amide. Next, we will be talking about a particular transformation in continuation with this is a Weinreb ketone synthesis. The disconnection is basically something like this. We said esters are very reactive. So, you need a softer reagent which are less active. So, you take the corresponding amide which is now named as Weinreb amide, react with a nucleophile, a Grignard or something. What will get? You basically get now the nucleophile, if it is having a metal containing nucleophile like lithium or magnesium, you will have a this kind of chelate. Now, this chelate is exceptionally stable, this chelate is exceptionally stable and that will stop the further nucleophilic addition. So, once you make this Weinreb amide, this will, if you use excess nucleophile does not matter, it will stop the reaction at this position. Now, you basically quench these things, your nucleophile will be definitely here. You quench with acidic workup, you will basically get the corresponding ketone back. So, coming to the original problem which was just discussing, the initial target molecule or initial intermediate after the Johnson Claisen thing, you getting this corresponding carboxylic acid, you hydrolyze this the acid with a base and react with this MENHOME which is the Weinreb amide or Weinreb amine, you will get the corresponding Weinreb amide. You react with methyl lithium or methyl magnesium bromide, you will get the target molecule. So, that basically completes the synthesis and the final compound is again a gamma delta unsaturated target molecule which is our main target, gamma delta unsaturated ketone, alpha, beta, gamma delta. So, Weinreb ketone synthesis was one of the important synthesis where you can essentially tune the reactivity of a amide. Esters are highly reactive, that is what if you are subjecting excess nucleophilic reagent like Grignard reagent to ester, that will give you tertiary alcohol. It will not stop the reaction at ketone point, but if you can convert the ester to a amide, mainly the Weinreb amide, the OMe group was judiciously chosen, the OMe group, and that is why the OMe group has been judiciously chosen to stop the reaction at the chelate stage. No matter if you can use excess nucleophilic species like Grignard, the reaction will stop here then you do the acidic quenching, you get the one equivalent of nucleophile transferred to the corresponding carbonyl compound, you will get the corresponding ketone. So, okay, next week we will be back with more problems, and we can discuss, or you can continue our discussion based on this transformation, functional group as well as static material based strategies. Hope you are enjoying the lecture. Thank you.